Hello everybody, so I'm Rei, I'm one of the co-founders and chief strategy officer of Tomorrow.io, and I lead our space program. First, I wanted to thank Ezanian for sharing their thoughts with us this morning. This was really insightful, so really appreciate you taking the time to talk with us. I want to start off by talking about why are we going to space, and we've obviously shared a bunch of these thoughts before, but I figure it's really good to just set the ground first and explain why does a software company decide to embark on this really challenging mission of building and launching satellites and operating them. And so the short answer to that question is really because we've identified a gigantic gap in observations that if we solve will create huge amount of value, societal value, and of course financial value, and that gap can only be solved from space. We've done a really large trade study and understanding who is doing stuff from space and what is planned, what can become, and realized that nobody was actually doing what we were planning to do, and so we decided to go to space. That's the short answer. And I guess that leads to explaining a little bit more about what's going on right now. I mean, obviously you might think, well, there are a lot of weather satellites out there already. Why more is needed, and why what we already have now is not solving everything. And so the really kind of short way of thinking about it is we do. We have a lot of weather and Earth observation satellites already on orbit today, and we've had them for many, many years. But the reality is that many of these satellites, or in fact all of them, do not really give us the full picture. And by the full picture, I mean they see certain parameters of the atmosphere, but they don't see all of them. And the stuff that they don't see, or they don't see good enough, is really what we're lacking. The best example of that would be precipitation, so rain, snow, hail, sleet, etc. We do not have today a good way or any real way of observing precipitation from space in a way that is useful for operational weather forecasting, meaning we don't see it frequently enough, or we don't see it in a way that is really clear enough to enable our forecasting models and to enable real-time applications. We have mostly infrared and electro-optical instruments on orbit, and those can see the clouds like you can see them with your own eyes, but they cannot see into the clouds. And so if we're seeing a cloud from above, we can't really say if it's precipitating or not, and we can't really say what's going on the ground where people live. This is just one of many examples, but the short summary is that state of observation from space today is still very lacking for weather forecasting. And so we decided to build our own constellation that will address that problem. And specifically what we're doing is we're building two types of instrument, two classes of instruments. One is called radar, which is an active sensor in the microwave frequency, microwave range. And the other one is called a sounder, which is a passive sensor in the same frequency range. And the reason we're doing two sensors is because that's really the best way to solve the problem of monitoring precipitation at a global scale with high refresh rate, high revisit rate, at a way that is actually practical. And so radars see certain part of it, they see precipitation in a very detailed way. The sounders see other elements of it, they see the humidity profiles, the temperature profiles, other types of weather parameters, and when you merge them, they're extremely powerful together. So it is indeed way more complicated to go after two separate types of sensors at the same time. Each of them is its own program with its own complexities and technical challenges and whatnot. But we're very much a problem-driven company, and so when we decided that that's a problem we're going to address and that this is the optimal technical solution, then execution is obviously secondary, and we're addressing all of these challenges. So this is why we're doing two types of sensors, because they really complement each other and enable us to achieve the best performance in terms of revisit rate, in terms of scan width, in terms of the types of observations we're looking within a given set of constraints of time and budget, etc. Now I want to talk a little bit about how what we're doing compares with what government agencies are doing, and we often get asked the question of, hey, why, if it's so important, why hasn't NOAA or NASA or the Europeans or the Japanese, why haven't they done it to date? And the answer to that is they've done parts of it, meaning they've built technology demonstrators that prove the concepts of everything we're building, but they haven't built full systems that support that kind of mission. And the reason is that it is hard, and it is really not aligned with how they're thinking of building weather satellites. Government agencies, if you're thinking about NOAA or others, they're very risk averse for a good reason. It's really justified. They want to build stuff that was already done and they know it's going to work, and they're not willing to take any risk, and they think about very long-term execution timelines. On the other side, private sector is much more willing to take technical risk and address stuff that was considered impossible before that. And probably the best example to that is reusable rockets from SpaceX, right? You might ask, well, why hasn't NASA built reusable rockets? Obviously, they've changed the entire industry. They took the launch cost down by so much. Why hasn't anybody done it before? Well, it's because it is risky, it is challenging, it is not the way government think, and therefore nobody has done it. But now that it exists, it is obvious and everybody is using it. It's exactly the same case with radar satellites for weather. Everybody see the value, everybody understand that it's going to completely change the game, but it is not the role of government agencies to go and really break into new frontiers in such a way. They have, and I want to emphasize it, NOAA, NASA, the Japanese, JAXA, and others, they have built groundbreaking instruments that prove those capabilities, but they're good for science missions, meaning they have very low revisit rates in the order of days. They see every point on Earth once every 3-4 days, and that is completely useless for the purpose of operational forecasting. When we run a forecasting model, we want the data to come in every hour, every 2 hours, every even few minutes, because the weather advances really quickly. That is a completely different game, moving from 3-4 days to hours. You need many more satellites, and to do that, you need to cut their cost down by quite a bit, and that is just not what government agencies and research institutions are set to do. And this is really where there is a great synergy between us as a private company and agencies like NASA and others. All in all, obviously, it is a very, very aggressive timeline, and we see infinite amount of challenges, execution challenges on supply chain, etc., that the entire space industry as a whole sees, but we're also seeing very fast progress. One question we get a lot, and I often get it personally a lot, is how is what you guys doing different from other weather companies? And I think that is something that if you're external to the industry, everything might sound similar, but the reality is quite different. So the weather industry, has been around for many decades. There are companies who've been here since the 60s, 70s, AccuWeather, IBM, the weather company, and so on. They've been around for quite some time. But you haven't seen them doing any of what we're doing, and especially not this really ambitious space mission. And the reason is they're really were focusing on repackaging governmental data, maybe adding some fine-tuning, some post-processing, whatnot, and then packing a lot of meteorologists on top of that to help you interpret that and help you make sense of this data. What we're doing is fundamentally different. We're looking at the entire value chain, from the observations to the hardcore numerical weather models, the global, the regional, all these pieces, and the products on top of that, the analytics. And we don't just say, well, we'll handle with what exists and give you the best repackaged product we can create. We're looking at the entire value chain and saying, how can we solve each of the pieces independently to make the whole much better? And so with regards to how this space mission is going to change our position and how is it different from others, this is building the infrastructure for a global weather system. Nobody's ever even tried to do anything remotely close to that. So think of having GPS as an example. It is a global infrastructure that we rely on for a whole bunch of applications that we don't even think of. Other than navigation, you can't swipe your credit card without a GPS. Think of that in the context of weather. What this system will enable, what this mission will enable, is crop insurance all around the globe, flood risk monitoring all around the world, aviation safety, not just within continental US or a few other countries that have good radar systems, but over the oceans and over Africa and over Latin America and all these regions. So there is a very long list of things that would be enabled by this system that nobody has ever really dreamed would be possible. And this is not a small differentiator. This is not, they're doing a model with 5 kilometer resolution and we're doing it with 3. This is just a completely different category of company, a completely different category of mission we're after, and that's really what sets us apart. With that, I want to talk about where we are. Where are we at the space program right now? So we've announced it a little over a year ago now, and obviously we've been working on it for much longer than that. It's been in stealth mode for quite some time before we shared it with the world. But let me just update you guys on what progress we've made since we've announced the program. So since then, we've made huge amounts of progress. We've hired more than 40 people to the team, and we are in build mode, meaning we already have the hardware being assembled together and tested, and we're planning to launch the first 2 satellites later this year and into early next year. These are the Pathfinders, as we call them, the first radar satellites, and we in parallel are working on satellite 3 onwards, which will be launched later on in 2023. That is the radar program. As I've said before, we've also recently shared that we're building another program, which is the Sounders one, and those satellites are actually being designed and built as we speak as well, and they're also planned to be launched late in 2023. So overall, we see great progress, and in fact, faster than I've ever dreamed we'll accomplish in such short time. And we still are on track to accomplish our goal of hitting 1 hour revisit rate globally by the end of 2024. I won't say there aren't challenges. Of course, there are. Space is really hard. We have supply chain challenges. We have launch availability, all sorts of difficulties. We are building hardware that's going to go to space. But I see really great capability, and the team is really amazing in their ability to overcome those challenges and really close these loops and getting us on time to meet our goal. So that's our timeline. Again, launching late this year and into 2023 and completing the mission by 2024. And aggressive, but very accomplishable, and we're very excited about it. Lastly, I want to talk about what is it going to do? What are the immediate applications of this data? So, we think about it really from a product standpoint. First and foremost, when I'm a user, what am I going to see? How is my app, my dashboard, my API going to be better? And there are a few ways to think about it, but the main one is we don't have radars in most parts of the world. So if you live or if you work in any of these regions that are outside the current radar coverage, your life with regards to weather are going to completely change, because this is moving from darkness to light, meaning you did not know if rain was going to come, you didn't have any type of flood forecasting, anything that is impacted by weather, you couldn't really see, and this is going to change it, right? So the immediate applications would really be just completely transforming the way weather is consumed in most parts of the world and what is possible. But I want to talk a little bit more about real concrete applications. So maybe I'll take a few examples. One would be flood forecasting. Floods are the most devastating and the most risky weather phenomena on the planet. They kill the most amount of people every year. But we still do not have a good way to forecast floods in most parts of the world, because floods starts from rain. If we don't know it's going to rain, we can't really say if it's going to flood. This is going to change. We're going to be able to provide accurate and point location flood forecast for every part on the globe in just a few years from now. This will save thousands of lives and billions of dollars in lost property, because we're going to be able to mobilize people and property ahead of those floods. That is maybe one example. Another example I want to share is regarding agriculture. Today, we have really hard time, again, in most parts of the world to provide accurate rainfall data for farmers and for financial institutions that insure these farmers and provide them with seeds and chemicals and finance support, etc. This is also going to change, because we are going to enable accurate rainfall measurement and prediction in any part of the globe. Last example I will give, and perhaps the most challenging of all, is improving the trajectory and intensity forecasting in tropical cyclones, so hurricanes, typhoons, etc. Today, we still do a pretty poor job at understanding whether it's going to be, a category 1, a category 3, or a category 5. And the implications on the ground for each of these scenarios are completely different. If we're thinking, category 1, we just, duck in a bit and it passes. But if it's a category 5, we need to evacuate an entire city. Today, we still are surprised by those changes, by those rapid intensification. This is going to change, but it is not only going to change in the US, it is going to change in India and in the Philippines and in Japan, in all the regions that are impacted by tropical cyclones all around the globe. This is a really challenging scientific task to solve it and really push forward those forecasts, but we're very excited about the possibilities with our new radars and sounders to improve the science here and improve eventually the forecast that people have. And so with that, I'll wrap. Thank you for listening and taking the time to learn more about our space program, and stay with us to learn about more updates. Thank you very much.
If you missed any of today's sessions, no problem. You can catch all of them at climacon.tomorrow.io on demand anytime you'd like.